This is an ant, this is a grain of salt, and this is a 01005 capacitor from your phone. On the phone's motherboard, which you can't see, there are a large number of such micro-components, each with a diameter about the size of a strand of hair. So here's the question. How are these components, which are completely invisible to the naked eye, soldered onto the phone's motherboard? In this video, we'll take a detailed look at the SMT surface mount technology process. Before SMT soldering, a stencil must be designed according to the motherboard that needs components mounted. After installing the stencil, the printer will first perform a cleaning cycle, using simultaneous exposure of the top and bottom plates to ensure there is no residual solder paste clogging the stencil, and to clean it if necessary. Next, the automatic solder paste dispenser squeezes the solder paste onto the stencil, much like squeezing toothpaste. Meanwhile, the motherboard is fed into the solder paste printer by the loader. The visual alignment system scans and aligns the stencil and the motherboard. Once everything is confirmed to be correct, the carrier platform rises to closely approach the stencil, and then the squeegee evenly spreads the solder paste across the holes in the stencil. The solder paste thickness inspection system on the squeegee uses lasers to synchronously control the thickness of the solder paste, ensuring an even coating. Of course, just ensuring the thickness isn't enough, the coverage also needs to be precise. Only with precise coverage can components of various sizes be soldered accurately. After the solder paste printing is completed, the motherboard is sent into the SPI inspection machine, which uses laser triangulation technology to check for any errors in the position of the pads and the coverage of the solder paste. Once the inspection is passed, the motherboard is sent to the most crucial step, the placement process. Do you remember the tiny components mentioned at the beginning? The placement machine uses vacuum suction to pick up the components. To precisely control the landing spot of each tiny component, high-precision sensors are installed on the placement head. These sensors monitor the entire process from picking up to placing the components, ensuring that each one lands exactly on the correct pad. These components, which are almost impossible to distinguish with the naked eye, are also scanned in 3D by high-precision cameras. Any components identified as defective are discarded, while those without issues have their orientation adjusted before being placed. When placing the component, the pickup head first quickly approaches the pad, then slows down, gently placing the component onto the pad at a low speed. When dealing with warped boards, the pickup head can also adjust the force from below to change the angle of the component, allowing it to fit perfectly onto the motherboard. The placement machine completes an entire cycle in just 0.08 seconds, which means it can handle 45,000 placements per hour. If this step were done manually, not to mention the accuracy, the time spent just on placing the components would be enough to produce an entire phone. After placement is complete, soldering cannot begin immediately. To promptly detect placement defects and ensure there is no need for rework, pre-reflow AOI, automated optical inspection, is required. A high-definition industrial camera scans the board, automatically comparing images to database parameters, preventing issues like slight misalignment, spontaneous countermeasures, missing placements, or multiple placements during mounting. Once the inspection is complete and no errors are found, the motherboard will enter the reflow soldering equipment. Reflow soldering consists of 4 sections: the preheating zone, the constant temperature zone, the heating zone, and the cooling zone. There is a common misconception here. Many people think that reflow soldering is simply a physical process where the solder paste softens and then solidifies again. In fact, reflow soldering also involves chemical reactions. When the board enters the preheating zone, in order to prevent warping or deformation of the board and thermal stress damage to the components, hot air will slowly heat the motherboard and its components. However, the heating cannot be too slow, and at this stage, the flux will also begin to evaporate. When the temperature reaches the constant temperature zone of 150 to 200 degrees Celsius, the flux on the surface of the motherboard is fully activated, removing oxides between the pads and components. This stage is maintained for 60 to 120 seconds, after which the temperature continues to rise to between 220 and 250 degrees Celsius. Entering the reflow zone, the temperature rises again. At this point, the solder paste undergoes a metallurgical reaction with the pads, forming a copper-tin alloy and achieving both electrical and mechanical connections. After reaching the peak temperature, the temperature begins to drop, and the motherboard undergoes forced convection cooling in the cooling zone. After coming out of the oven, the components are firmly soldered onto the motherboard, but the process is not considered complete until they pass through post-reflow AOI. The post-reflow AOI uses high-definition CCD industrial cameras to capture detailed images of the solder joints and components, simulates the 3-dimensional shape of the solder joints, and then uses image algorithms to ensure that every solder joint is free of defects. Finally, the motherboards that pass inspection are transferred to the carrier rack, ready to be sent to the next stage of testing.